Hi, in this video we'll be going through what are the isomorphism theorems in group theory. So let's begin by first defining what an isomorphism is. If you recall from previous video, we have shown that if a map is a homeomorphism, then its inverse is also a homeomorphism. And so we can now define an isomorphism to be a function that is both a bijection and a homeomorphism. And so the inverse of this function now will be homeomorphism. And so when two groups are isomorphic to each other, we say that there is a bijection that preserves the group operation. And this means really that G and H have the same group structure. It's just a renaming of the elements in G and H. So the properties of the group will now depend on its group structure, and so G and H will have the same group properties. And hence, understanding how the group works, G works, will help us understand how H works and vice versa. And so what we really want to say is that we want to have a group that we can easily understand, and then show that any other group that looks complicated is isomorphic to this group, and as a result, all the harder groups we can just understand it because we understand the simpler group. And this is a central problem in group theory, is to prove the isomorphism classifications. And these classifications are really saying that if G is an object with some property, then where are the other objects that have the same property? And by same we mean isomorphic to G. Some examples will include that any non-abelian group of order 6 will then be isomorphic to S3. So S3 is the permutation group with 3 elements. And so other examples of isomorphic groups will be, of course, G will be isomorphic to itself. The real numbers with addition is isomorphic to the positive real numbers with multiplication. Just use the map EX. And now we can say that the set of cosets Z over NZ, so this is the quotient group, is isomorphic to the remainders of n in the integers. And so now you can see how this group now, once we study this group and we just show it's isomorphic to this, we understand how this quotient group works, and it's basically the set of remainders. And you can just think of it as the set of remainders instead of always thinking as the set of cosets of nx, nz. And so now really, how do we want to help us in finding isomorphisms? Well, we can really use the isomorphism theorems. And so let's begin. There are 4 in general. So the first isomorphism theorem states that if phi is a function from G to H and is a homeomorphism, and the kernel of phi will now be normal in G, then G of the quotient of phi, G quotient of phi, the kernel of phi, will be isomorphic to the image of G in phi. So how do we prove this? Well, first we consider the map from G quotient, the kernel of phi, to the map of the image of G. And we just define alpha as, so this is the element in the coset, so it's G kernel of this phi, to just equals to phi of G. So G being here, so this is the image. Then two cosets are equal if and only if H inverse G is the element of the kernel. And this is only true if and only if the image equals to 1. And so, because it's a homomorphism, this means that the phi of G equals to the phi of H. And what is the phi of G? It is defined as alpha G kernel phi equals to alpha H kernel phi. And so this proves that if two particular elements are equivalent, then their images will be equivalent. And so alpha is well defined. This also shows that it is injective because when the images equal, then the elements must equal to each other. And then it's clear that phi is subjective because any element here can be found in here, since phi of G will be like a subset of H. So now this shows that alpha is bijective, and hence you have an isomorphism between these two. So the last thing to check is this isomorphism that we're trying to get is also a homomorphism. So what we need to say now is we just take two elements in the coset and we just group operation them, and you take the image and you just show that the image respects group operation. And because alpha is a group homomorphism, these two are isomorphic to each other. And so we're just saying that G, quotient of the kernel, will just be isomorphic to the image. And a corollary of it is really saying that now phi is injective if and only if the kernel equals to 1. Because if phi is injective, then the image, the G will be isomorphic to the image itself. And so the kernel has to be the trivial group. This also states that the number of cosets of G quotient of the kernel of phi is just phi of G. So with the first isomorphism theorem down, we shall move on to the second isomorphism theorem. And it states that AB quotient of B will be isomorphic to A quotient of A intersect B. And really, you can just think of it in the terms of the normalizer, and you just need to create a suitable map such that the quotient of this map A to AB slash B, the quotient of this, the kernel of this map, you realize is A intersect B. And so, as a result, you just use the first isomorphism theorem to prove they're isomorphic to each other. So you can now actually read the proof here, and when you understand it, you realize it's really just an application of the first isomorphism theorem. Well, we move on to the third isomorphism theorem, and you can just think of it as like to remember easily, as a way of remembering only. You can just think of it as a fraction. And what we really want to say is that G quotient H, and then you quotient it with H quotient H, K quotient H, you'll be just isomorphic to G quotient of H, K. So we denote the quotient by H with a bar. You can just write it as the following. And it's easy to check now that this map is well defined and there is a bijection between them. And then you just apply the first isomorphism theorem to take this divided by the quotient of the phi and see what remains. And you can just check that the kernel of 5 will equals to the following K over K quotient of H. And so by the first isomorphism, you already get the answer we want. So what we can really say now with the third isomorphism theorem is that you gain no new structural information from taking the quotient of a quotient group. Because what we will have, let's say, is G quotient K. And we think it's easier if we take the quotient first of a group that we may understand, and then we quotient it off with K quotient H again. And then we just show that it will be just isomorphic to G quotient K. So we are back to the same problem. So really we gain no new structural information. So this is the third isomorphism theorem. And the last one we'll go through is the fourth isomorphism theorem, also known as the lattice isomorphism theorem. And you really think of it as a lattice later on. And for this one, we'll leave the proof into the textbook for you to try it out and read on your own. But really, if we let G be a group and N be a normal subgroup of G, then we can actually say that there is a bijection between the subgroups in G containing this N and the set of subgroups in the quotient group of G quotient N. And so in particular, every subgroup of the quotient group is of the form A quotient N for some subgroup A containing N. And this bijection has a very nice property such that if A is a subgroup of B, then the quotient subgroup A is a subgroup of the quotient subgroup of B. And if A is normal, then the quotient in the quotient group, it will be normal as well. And so simply put it, you can just say that the subgroups of G quotient N are of the form H quotient N. And then just H is a subgroup N, and N is a subset of H, and H is a subgroup of G. So you can just think of it in this form, and you can just switch between the two. And so we are saying that it describes a relation between the subgroups of the quotient group and the structure of the subgroups of G. And really, the lattice of G quotient N can be read off immediately from the lattice for G by collapsing all the groups N to become the identity. So what we want to say from this paragraph in Dummer and Foot is, if we take a group G and we have some subgroups here, H1, H2, H3, and all of them contain N, then what we are saying is that when we take the quotient G quotient N, it has to be coming, all the subgroups must be the one that only contain N. So you cannot have like a subgroup below N in the quotient group. So you can just see now the quotient group here, it will be lying in here. So this part represents your quotient group. So everything above N. So that's why it's known as the lattice isomorphism theorem, because it really can visualize it in terms of the lattice structure. So this is the last isomorphism theorem we'll go through. And with these 4 isomorphism theorems, you can now try out problems in Dummer and Foot to really practice on finding isomorphism types. So this is all for this video. I'll catch you in the next one, and I hope you have enjoyed it. See you!